Okay, in this assignment, we're creating the skeleton of a multiplayer game. I have here two clients running on my computer. The server is actually located on another computer so that all communication is going over a physical network. The reason I have the two clients running on this single computer is purely because it allows me to see what's going on. I can see the results of moving around and seeing what happens in the other window. So without further ado, let's give that a go. So I'm selecting this client over here, moving around the avatar. You can see I see the movement of the avatar over there. Likewise, I see this guy now moving along and now moving through in the other window. So you can see that what's going on is that we indeed have multiplayer interaction, although two of the clients on a single machine. There's no reason why I couldn't run this with the two clients on different machines. It just would, again, make it difficult to set up and make it difficult to see what's actually happening. In addition, it is theoretically possible to run two clients and the server on one computer, which for testing purposes is reasonable enough. Just be aware that it takes a fairly beefy client to be able to run three instances of a Unity program all at the same time. Now, let's look at this movement here. So I'm going to move this guy here. And you can see as this is going that the movement is, although it gets the job done, it's not exactly perfect. The movement of this guy as we're moving around is awfully jerky. And the reason for that is that I'm by default sending messages across the network every 200 milliseconds. And that means that the positional update on the other client is limited to once every 200 milliseconds, which means that the avatar is jumping about quite a bit with each move. So if you think this is probably running at about 60 frames a second, but the avatar is moving only every 200 milliseconds as those network messages coming through. So up here I have provided a drop down that allows us to select between different algorithms. So here's a dead reckoning algorithm, and I think if we give this a try, we can see that what dead reckoning does is in the frames where we don't have a new position, we guess the position, and we can see that's now looking a lot more smooth. And it's simply because each time when we don't know the position, then we're guessing based on our previous direction and speed. And so we can see this guy here, again, his movement is much smoother. Now you can see that one thing that's missing in this particular implementation is that we don't have smooth rotation. So the rotation is still jerky. I didn't do extrapolation on the movement, on the rotational movement, just on the forward movement. Now, watch what happens when this guy stops. You can see this is the main bug in predictive approaches. So I'm going to move him forward and then stop, and watch this guy as he moves forward, and then I'm going to stop him about here and then see what happens. Okay, so that worked about okay. Actually, now it's not happening because I'm trying to demo this idea. Yeah, there you saw it right there, that he moves forward and he walks a little bit too far and then jumps back. There we saw a nice good example of it there. So what's happening there is that the dead reckoning algorithm is assuming that he's keeping on walking in the absence of other information. He gets a message realizing that he stopped and then snaps him back to his previous position. And so I've got this slider here is going to show it even more clearly. So the slider here is representing the frequency with which messages are sent from the client to the server. So by default, the first notch here is 200 milliseconds. If I move this over to 0 milliseconds, it's basically going to send messages as fast as it can. And then up to the maximum is 1000 milliseconds, meaning that only one positional update per second is being sent. And so that's going to make it much more extreme, this notion of what's happening. So yeah, you can see there that there's a bigger delay in getting messages across because we're only sending messages once a second. And then that snapping business is much more extreme, and that's really because, there we go, see how much he snapped there? Because if we're unlucky and then we have a full second's worth of movement that we have to compensate for. So, as discussed in class, we can compensate from that with a smooth corrections algorithm. And so what's going to happen here is that we're going to move this guy forward. If we realize that we're going to continue to use dead reckoning, and if we realize that dead reckoning has misled us and put us into the wrong position, then the guy will actually turn to the position he's meant to be in, walk really quickly to that position, and then stop. So let's see if we can get that to show up nicely. Did you see that? He turned, ran back, and then went to the correct position. There we go. So that's an example of a smooth correction. Let's see if we can get that to happen a bit more. Okay, so very speedy correction of a bad position. So that's what we're going to be doing in this assignment. I've given you some code that gives you a little bit of the framework to help out with this, so you're not having to build everything from scratch. You're going to be filling in a lot of the networking code and a lot of the code to do the dead reckoning and to do the smooth corrections.